Hello everybody, back to Chapter 1 notes. And now we're in graphing, or at least being able to take a look at an equation and see what kind of graph it will make. And so, why do we graph at all? Well, it's so that we can see how two things change with respect to each other. I remember learning about graphing when I was in elementary school, or maybe middle school, and just thinking it was a way to draw cool things on on an axis like this, almost as if the drawing itself were the end product. Rather, it's the graph itself. It's the shape of this or the shape of this that tells us what's happening in an equation. That is how two things, how this y-axis and how this x-axis relate to each other. One kind of graph we're going to focus on a lot is this one right here, a linear graph. This curved one, this very poorly drawn parabola, is another kind of graph, certainly not linear. But linear graphs tell us that as x changes, y changes a proportional way to that. And so graphing helps us to see how two values change with respect to each other. And so the purpose of this section is to be able to look at a kind of equation and figure out what it would make just by looking at it. And here's a couple of examples here. First of all, a linear equation. You can see clearly the line is straight, that's why we call it linear. And so equations that go kind of like y is proportional directly to x. This little thing right here, this means proportional. You could really plug in an equals sign there if you wanted to, but it doesn't have to be an equals. So proportional means is kind of related to x. That means it's related to x in a direct way. As y changes, x changes, and nothing else changes, you might want to say. They increase or decrease proportionally to each other. The second one right here, that is the one over on the right, you might recognize this. Well, actually, it's kind of a little too round, but this should be a parabola. I just talked about a poorly drawn parabola that I did. This one isn't too great either. But if you were to punch in on your graphing calculator y equals x squared, right, you'd actually have this parabola. Actually, it would be centered right on the y-axis, kind of like, I didn't even have it touch the bottom either. Let me try that again. You'd have it centered right on the y-axis. Finish that little parenthesis there. There we go. It would look kind of like, let's start from this side. Still pretty weak, but you get the idea. It would be centered right on that y-axis. Y equals x squared. That certainly is not linear. It is a what we call a square relationship, but you would get that kind of open-ended graph where it's either open at the top, or in some cases it might be open at the bottom. That's a little better. Why couldn't I do that earlier? I can draw that better next time. All right. The only reason this is shifted over here, over to the right, is because, well, for this top equation right here, y equals, or y is proportional to x squared plus x. That plus x shifts the graph one way or the other. But generally speaking, if you have a square, right, y is equal or proportional to x squared, you're going to have an open-ended, either open on the top or open on the bottom type graph. All right, down to the lower left. Here we have an inverse relationship. All right, so as y changes, x changes inversely proportionally to that. Take a look at this, for example. If we were just to plug in some values right here, if we were to plug in, I don't know, 10, all right, for y, all right, then x would be a certain value. If y were to increase, then that means x were to have to decrease because it's in the denominator right here. All right, because in the denominator, we're having 1 divided by x. So I don't know why I just said 10 a minute ago. I'm not really plugging in numbers right here. But these are inversely proportional to each other. So as y goes up, x goes down. As x goes up, y goes down. And the graph tells that right here. The less x is, the greater y is. As x increases, y gets less and less and less. So we call that an inversely proportional graph, or an inverse relationship, or an inverse proportionality. This last one right here is a square root proportionality. So if on your graphic calculators, if you were to punch in y is equal to the square root of x, you would get something kind of like this, like a sideways opening graph. You can't have a square root of a negative number, and so the bottom half of this isn't here. You can kind of play games with your calculator a little bit and force that bottom part of the parabola to be in there. But you can see, generally speaking, it would open to the right or open to the left. We would call that a square, or an inverse, a square relationship. Sorry, these are inverse over here. This would be an square. All right. So we care about linear relationships a lot, and we call them directly proportional relationships if they form a linear graph. And those we like a lot because they fit our y equals mx plus b model. A linear equation creates a linear graph. And you know, in just a minute, I'm going to say this m is pretty important. Y is one value, x is the other value. B, of course, you need to be something else, which we'll talk about in just a second. But that all-important m, that tells you the whole story around the relationship between y and what is that? Of course, you know that the m is the slope. It's the rise over the run. So if I just, I'm just going to draw a random, right there, a random linear line. For every x value, why is that not writing? Try that again. Kind of writing, all right? For every x distance, there's a corresponding y distance, whether it's right there or right here. Now, mine isn't perfectly drawn, but you get the idea. X to y, whether you make a big X or a small x, a big Y, a small y, it's always going to be the same relationship. That rise over the run, or the change in y over change in x, is always going to be the same, because that line, if I drew it straight enough, that line is not changing its slope. Its slope is constant. All right? Now, I mentioned b earlier on, y equals mx plus b. Of course, you know b is the y-intercept. That is where the graph happens to cross the y-axis when x equals 0. At x equals 0, that's where we tend to draw the y-axis vertically. And if you plug in x, or if you plug in 0 for x, wherever the graph crosses the y-axis, that's what you call the y-intercept. All right. So if we have a positive slope, that is, if m is greater than 0, if it's 1, 2, 3, or 4, etc., then it will slope up. That is, if we're moving from left to right, it will slope up in that direction right there. All right? And the greater the value of m, and hopefully you know what these things are right here. That means absolute value, right? You can have a positive m or a negative m. Either way, the greater that value, or the greater the absolute value, the steeper the graph will appear. All right, so we have m, so we say we have small m here, okay, a smallish m. You'll have a graph kind of like that. The bigger m gets, I'll make a big lowercase m right there, it's going to be much steeper. A greater rise for a given run. Okay, so let's do a couple of examples right here. We have y equals 1/2 x. Now remember, if we use the formula y equals mx plus b, all right, b is the y-intercept, b is the y-intercept, m is the slope right there. So whatever is being multiplied by x is in fact the slope, or what we call rise over run sometimes. So here we've got y, okay, excuse me, my dog just jumped up into my lap right here. Go sit down, please. Thank you. Y equals 1, yes, you're lovely. Get out of here. Sorry, you're probably laughing right now. Y equals 1/2 x. So I'm gonna bracket this off in green, all right? 1/2 x. What's our rise over our run? Well, we're saying that we've got a rise of 1 for every run, that's a tongue twister, of 2. All right, so for that first one right there, I'm going to draw that one in blue, okay? Let's make a couple notches right here. 1, 2, 3, 4, 5, and 1, 2, that should be enough, I think. 3, 4, 5. So then that means that we rise 1 and go over 2, or over 2 and rise 1. I don't care what, well, it actually is x and then y, but so we go over 2 and up 1. So starting at the origin right there, we would put our dot right here. Okay? Over 2 and up 1, put our dot right here. Over another 2 and up 1, you get the main idea, all right? So that is going to be our slope for that first one. Secondly, what if y equals x? All right, well, that, you're like, oh, what's the m? What's the coefficient? Well, it's 1, of course, right? Because, let's make this one red. That's like saying that's 1 right there. So for every 1x, there's 1y. All right, so we go over x and up y, 1. Over 1x, up 1y, 1 over 1. You see where this is going, okay? So just like that. And then this one right here, I'll make this one green. Y equals 2x. You could say that's 2 over 1. So a run of 1 in the x direction and a rise of 2 in the y direction. So over 1 and up 2, you can see right away, since that 2 is the greatest coefficient right there, it's going to result in the steepest slope. Just like that. All right? Easy. Let's go to the next one. My dog finally jumped off my lap now. Yes, thank you. All right. Y equals x. We just did that a minute ago, okay? Over 1, up 1. Why is that not drawing? Just erase that right there. Sorry. And if you're just jumping ahead of me, you're more than welcome to, because you probably know where this is going. Over 1, up 1, let's make that green. So it'll look like that. All right? But here now we have a negative in front of the x, or you might say a negative 1 right there in front of the x. So that means it will go down, it will drop 1y for every x. So in this case, if we're going to make this one red, it simply slopes down the opposite direction. Over x, it drops 1y. Over 1x, drops 1y. Over 1x and drops 1y, etc. So that would be, ugh, that was pretty poorly drawn. Hopefully you can envision that going through all the red dots. Now, this last one right here, I'm going to do in blue. We have y is negative 2x. So the negative says it's going to slope down as we go left to right. And the 2, remember we said the absolute value, the greater the absolute value, means that it's going to be steeper. So that means we go over 1 and down 2. I didn't put notches here on this lower line, but I'm sure you can probably envision this. Over 1, down 2. Over 1, down 2. So this is going to be a much steeper, albeit negative, slope going down just like that. Man, I don't think I could draw a worse blue line. Let's try that one more time right here. Actually, it wasn't too bad when I do that. All right, so let's try it one more time. Don't want that to happen. Pen, there we go. It would be like that. Steeper slope, but it happens to be negative. All right. Last one we're going to do is look at all these here. What's similar about them? They all have the same coefficient out in front of the x, right? And the coefficient is 1. There is no other whole number in front of the x. It's simply just 1. So all these are going to have a slope of 1. Over 1, up 1. Over 1, up 1. 1 rise, 1 run. But what's different is, of course, well, this one has no y-intercept. This one has one of positive 1. This one has one of negative 1. So let's do this one in red, this one in blue, and this one in green. So I'm going to draw a few notches right here just to kind of get our bearings. All right, 1, 2, 3, 1, 2, 3. And that first red one, I'm going to do y equals x. That's easy. Over 1, up 1, over 1, up 1, over 1, up 1. And since the y-intercept is non-existent, it's 0, it should go right through 0. All right? The second one is exactly the same, but it has a y-intercept of 1, which means the whole entire graph is going to be shifted up 1. So it's going to parallel this first one, but it's going to be shifted up 1. And this last one right here, will you guys stop it? Get out of here. the y-intercept is -1, right? So the whole graph is going to be shifted. I'll draw a little negative notch right there. The whole graph is going to be shifted into the negative y-axis, but they will all have the exact same slope and all be parallel because it's that same coefficient out there. This doesn't look very much like a 1, but that's supposed to be a 1 right there. All right, so that's linear graphing. And your homework, when I assign it to you, is going to be the first part of homework 1-4, which all deals with linear graphs. And you're going to need to be able to sketch them. So if you need to, you can refer back to this. But for the time being, that's it. I'll see you in class.